This is my answer for homework 11, question number 1. So the question says that x of t is a real wide-sense stationary process with autocorrelation tau and spectral density of omega. So the first part of the question says, show that the autocorrelation tau is real and even. So that's the question. So then if something's even, that means that the autocorrelation tau is equal to the autocorrelation of negative tau. And so to prove that, we have the autocorrelation tau is equal to the expectation of x of t times the expectation of x of t times x of t plus tau, because in a wide-sense stationary process, it's independent of tau. And so that is equal to the expectation of x of t minus tau. So basically we just take tau away from both sides, and you multiply that by x of t plus tau minus tau, because we took away tau from both sides. And so we're allowed to do this because, like I said, the wide-sense stationary process means that the time shift does not impact. And also, these are both real processes. And so then that ends up being equal to the autocorrelation of negative tau. And so both sides are equal, which proves that the autocorrelation tau is real and even. The second part of the question says to show that the spectral density of omega is even and non-negative. So we can show that it is even so here I have a few notes. So we have the spectral density is the Fourier transform of the autocorrelation. And so that's another way to rewrite it, where I subbed in f for omega. So we have the integral from negative infinity to infinity of the autocorrelation tau times e to the negative j times 2 pi omega, or f, times tau delta tau. And so we know that for something to be even, it's got to look like the autocorrelation of tau is equal to the autocorrelation of negative tau. Therefore, the spectral density of omega is equal to negative infinity to infinity of the autocorrelation tau times cosine times omega tau plus j times sine of omega times tau times delta tau, which is equal to the integral from negative infinity to infinity of the autocorrelation tau times the cosine of omega times tau delta tau. And that is equal to 2 times the integral from 0 to infinity of the autocorrelation tau times the cosine of omega times tau delta tau, which is also equal to 2 times the integral of 0 to infinity, the autocorrelation tau times the cosine of negative omega tau delta tau. And so because of that, or that can also be rewritten as the spectral density of negative omega, which is equal to the spectral density of omega, which means that spectral density is even. And so to show that the spectral density is non-negative, it's a little bit harder to prove in like a left side equals right side format, so it's better to use an example. So we consider an ideal bandpass filter with output y of t is equal to h of t times, or h of t convolution of x of t, where x of t is a wide-sense stationary process. And so to find the average power of x of t in the band, and we write the band as the interval from omega 1 to omega 2, we calculate the expectation of y squared t, which is equal to the integral from negative infinity to infinity of the spectral density of omega delta omega, and that's equal to the integral of negative infinity to infinity of h of omega, the absolute value of h of omega squared times spectral density of x of omega. And that's equal to the integral from negative omega 2 to negative omega 1 of the spectral density of omega delta omega plus the integral from positive omega 2 to positive omega 1 of the spectral density x of omega delta omega And we can rewrite that as 2 times the positive integral, or 2 times the integral of positive omega 1 to omega 2 spectral density x of omega, which must always be equal or greater to 0 for all omegas. And so another way to, I guess, prove this is if we draw it out, we can see that the area of the portion of the filter that we're talking about, the band interval, must always be positive. And so that proves that the spectral density is both even and non-negative.